Again, we start from the beginning of chapter 12. In sorry, 11. In chapter 11, we said that we have a simple linear regression model explained by this equation on this slide. In this simple linear equation, we have two unknown quantities, beta naught and beta 1. We want to estimate them. And we derived the estimated quantities to be these formulas in the yellow. Once we estimated these quantities, we call them point estimates. To extend the point estimates to interval estimates, we needed the sampling distributions of these point estimates. We derived those sampling distributions of the point estimates here in this slide. Here are the sampling distributions. From these sampling distributions, we converted the point estimates to interval estimates. Also, we wrote down the formulas for test statistic if you are interested in any test related to them. Then we had a problem. The problem was that in all these sampling distribution formulas, there was an unknown quantity sigma square. To get that unknown quantity sigma square, we derived its formula. Its formula came out to be SSE divided by n minus 2. Where it is? It is here. Once we wrote down its formula, the sigma hat square to be SSE over n minus 2, we observed that getting the process of getting SSE was very long. Fit the regression, get the fitted values, get the errors, square the errors, and so on. So we tried to look for a shortcut method. And that shortcut method again was driven by this equation, y equals beta naught plus beta 1x plus epsilon. It is driven by this equation, which says that the total variation in y is equal to the variation which is explained by your regression and the variation which is not explained by your regression. The total variation is denoted by SST. The regression sum of square SSR is the variation which is explained by your regression, and SSE is the part which is not explained by your regression. Luckily, your formula sheet gives you the formulas for SST and for SSR, which is SST equals this thing and SSR equals this thing. So you can manipulate this equation to solve it for SSE using a shortcut method. Clear? Now, this equation also leads you towards another concept, which is, again, I will write this equation here somewhere. Yeah, it is here. Now, we have this equation that the total variation in y is equal to the variation explained by your regression plus the variation not explained by your regression. And can you guess what is the abbreviation for SST? What does SST stand for? SST stand for S for sum, second S for square, and T for sure. So it's a sum of squares. What does SSR stand for? What does SSE stand for? These are all sum of squares. Can squares be negative? That means these three quantities are all positive, correct? Now, here is a catch. The total variation in y, suppose it is SST, okay? Now, some variation in y will be explained by your regression, some will not be explained by your regression. So suppose if nothing is explained by your regression and you have a very, very bad regression, what will happen in that case? If you have a very, very bad regression, error will be all of it and SSR will be 0. No variation explained by your regression. Everything went to the error. Very, very bad regression. And if you have a very, very good regression, mathematical relationship, SSR will be not one, sorry, whole SST. SSE will be 0, right? So in a sense, you can even judge if your regression is good or not using this equation. Using this equation, you can judge if the regression is good or bad. So this equation also serves as a measure of goodness of the regression. How good is your regression? But what is the scale of 0 and SST? What if SSR is 0.4? Is this big enough to say that regression is good? What if it is 1.3? Is it good enough to say regression is good? What if it is 2.5, 7.9? Because it can be anywhere from 0 to SST, correct? So can you draw, or can you standardize it or scale it in a better way? Here, this is a very unscaled version to just look at SSR in a raw form. It's very difficult to judge if it is a big value or a small value. Differentiating between the value, if it is close to 0 or not, is difficult. But if you look at SSR in comparison to SST, that is, you divide SSR by SST, what does it become? It becomes a nice ratio between 0 and 1 because SSR is a part of SST, correct? So in case SSR is 0, the ratio will be 0. In case SSR is SST, the ratio will be 1. So now you have a nice ratio that is bounded between 0 and 1, where 0 indicates that none of the variation in Y was explained by your regression. 1 indicates that 100% of the variation in Y is explained by your regression. In between, if the value is, let's say, 0.9, that means 90% of the variation in Y is explained by the regression. If the value of this measure is 0.7, that means 70% of the variation is explained by your regression. What about the remaining 30%? Not explained by your regression, or it goes to the error. So this again will be one of the concepts tested in exam, that what is R square? We call it R square. R square is the proportion of variation in Y which is explained by your regression. It is a square. I will not write the formulas, but it is a square. Look here. The formula for SST is summation yi minus y bar whole square. The formula for SSE is summation yi minus yi hat whole square, sum of squares of errors. It's a square. Summation. The formula for SSR is this is SSR, this is SSE, and this is SST. Again, the formulas that you get in the formula sheet, they are simplified versions of these. Simplified versions of these. But originally, they are all squares. Again, we have not discussed what is R yet. We don't know what is R yet. I introduced R square for a moment. Now, he brought the discussion of R. Now you know there is something called correlation between the two variables. Call it luckily or unluckily, this R square becomes the square of that correlation. But it's mere coincidence. It's no concept behind it, and it's only applicable for chapter 11. Once you go to chapter 12, you will have many features. Okay. And there you will not have the concept of correlation. There you will only talk about this R square. So for chapter 11 only, this R square that you will get, luckily, again, there is a background mathematical derivation. Luckily, it is simply the square of the correlation between the two variables X and Y. Okay. Luckily, no concept behind it. Okay, let's move on. Moving on, if you are interested in testing if the regression is good or bad, there is a formal F test. And this F test is based on the ratio between explained variation and unexplained variation. The ratio between explained variation and unexplained variation. Now, again, I take the SSR, which is the explained variation. I divide it by the number of features. For chapter 11, how many features do we have? 1. The variables on the right side, features, predictors. I have 1 predictor. If you divide the sum by the number, what do you get? Summation x divided by n. If you divide the sum by the number, what do you get? Average. So the sum of squares of regression divided by how many features are contributing, this will give you the average contribution per feature. What we call mean square regression. Average explained variation. Sum of squares of error divided by its degree of freedom. This gives you mean square error. Now, if you put these two in terms of a ratio, now let me show you what happens to this ratio. Okay. Now let's talk about one of the extreme situations where your regression is very bad. If your regression is very bad, what will happen to SSR? It will be approximately 0. And if your regression is very, very good, what happens to SSE? If your regression is very, very good, what happens to error? It will be almost 0. And what happens to the ratio? Something divided by 0. Infinity, right? So I define a ratio, I call it f. Now this f is from 0 to infinity. 0 indicates what? Very, very bad, insignificant regression. The regression is insignificant. It's not good. Infinity indicates what? Or a big value of f indicates what? It's a good regression. In between 0 and infinity, there is a cutoff. This cutoff is called critical value. Critical value. We have been dealing with the critical values, yes? This cutoff is called critical value. It comes from the F table. We'll give you the third table, which is called after Z and T. We'll give you a third table, which is called F table. This critical value comes from the F table. Now, if the computed value of F from your regression is on the left side of this critical value, you will say that the regression is bad, insignificant. If the value of F is large, you will say the regression is good. And apart from the critical value approach, you also have the p-value approach, which you can implement, where the p-value of this test is the probability in F distribution to get area above this calculated value of F. We will compute both of these two in examples, and I will show you how to test the significance of the whole regression using F test. Using F test, you can test it. But sometimes you get a question in exam where the question asks you don't rely on the table. The question gives you a value either very, very close to 0 or very, very close to infinity, like 7,000. If the value of F is 7,000, straight away you should say the regression is good, significant, because this is very big. If the value of F is 0.002, straight away it's very close to 0. The critical values are usually 2 point something, 3 point something, 4 point something. Usually from F table, the critical values are like this one. So if the value is very close to 0, immediately you should get an impression that regression is bad. If the value of F is very close to infinity, immediately you should get an impression that the regression is very, very good. We will continue with this one in the examples. Then there was a concept of correlation here in this slide. Sometimes you are not interested in regression. Sometimes you're not interested in what variable is input, what variable is output. Both of the variables are just the variables for you. And you are not interested in a regression line. You are only interested to see how strongly are they correlated. In that case, you find a measure that is called coefficient of correlation. Here is the formula for the coefficient of correlation. Again, it depends upon SXX, SSYY, and SXY. So you find those sums from the data and plug it in. What is the possible domain for this R? Not 0 to 1. -1 to 1. Where the sign of this correlation indicates what? Sign, plus or minus. It indicates the direction of relationship between the two variables. And the value indicates what? The strength of the relationship. So if R is 0.1, what does that mean? Weak positive. Weak positive if it is minus 0.1. Weak negative if it is plus 0.9. Strong positive minus 0.9. So R has two things. Number one, it has a value. Number two, it has a sign. Sign indicates the direction of relationship. If sign is negative, that means if one variable increases, the other one decreases, or if the first one decreases, the other one increases, they move in the opposite direction. That's a negative relationship. And positive means if one increases, the other also increases, or if one decreases, the other also decreases. That's a positive relationship. One of the things that usually the students, they get it wrong in exam. You get a question that if x decreases, y also decreases. Is this a positive relationship or a negative relationship? It's a positive, it's not negative. If x decreases and y also decreases, they are moving in the same direction. Correlation should be positive in this. Sometimes you are interested in testing hypothesis about whether the correlation is close to zero or not. The population correlation is denoted by rho, and the sample correlation is denoted by R. Like the population mean is denoted by mu, sample mean is denoted by X bar. Population variance is denoted by sigma square. Sample variance is denoted by S square. Population intercept is denoted by beta naught. Sample intercept is denoted by beta naught hat. Population slope is denoted by beta 1. Sample slope is denoted by beta 1 hat. Some books call it 1. Some books call it B1. Some books call it beta 1 hat. Your book call it beta 1 hat. So for every unknown quantity in the population, there is a point estimate in the sample. Rho is an unknown quantity. R is an estimate for that one. So sometimes you're interested in testing whether the correlation is zero or not. For that one, we have a T statistic. So you will find the value of correlation and plug it into the T statistic. And then you can either use the critical region or p-value approach that we discussed in chapter 5 to come up with the conclusion. Again, the same decision rules, same T statistic, everything is same from chapter 9. But one thing you need to understand is that this slide can only be used to test rho equals 0. If you are interested in testing that rho is 0.5, you cannot use this test. It is only useful for if the right side of H0 and H1 is 0. Only possible against 0. Not against any other number. For other numbers, there is another Z, approximate Z test, which is not in your syllabus. Okay, which is not in your syllabus. So if you are interested in testing if rho is 0.5 against not 0.5, you can test it using another test, which is not in the syllabus. After you did everything with the regression, then you did what? You said the regression is ready for the use. What were the two uses of regression? Very, very important. For sure, there will be a question from this concept in exam. Two uses of regression. One is for predicting a single value of y when x is x naught, and one is to estimate the mean value of y when x is x naught. Fortunately, the point estimate for both of them are same, but the interval estimates are different. One of the hints you will get in exam. Now listen carefully. One of the hints you will get in exam. Here are the two of them. Here are the two of them. The top one is the interval estimate for the mean of y when x is x naught. The lower one is the interval estimate for single value of y when x is x naught. And I said that these point estimates are same. The yellow ones are same, but the overall interval will not be the same. One hint that you might get an exam question, if it says prediction interval, that means it is referring to single observation. If it uses the word confidence interval, that means it's referring to mean response. Okay, but sometimes if the question they want to make it tough, they don't use prediction interval, they don't use confidence interval, they use the word interval estimate, which applies to both of them. Then you have to read the statement very carefully whether the question is about the mean of y or single value of y. Mean of y or single value of y. If the question is about mean of y, the first one will be applied. If the question is about single value of y, the second one will be applied. Okay. I will show you the examples of these in the upcoming problems. Now let us move on towards the example, the all important example. This is an example where the data comes from an experiment where the chemical engineer measured the purity of oxygen, which is Y, produced in a chemical process at different hydrocarbon levels. I have no idea about the relationship. The chemical engineers can explain what is the nature of relationship going on. Looking at these data, the first thing they asked us to do is they asked us to draw a scatter plot of the data. So when we drew the scatter plot of the data, here is the scatter plot. From this scatter plot, what do you get? If I try to pass through a straight line from these data, can I pass through? Approximately, right? Approximately. So there is a linear, a positive linear association between X and Y. And it is not very strong, but it is good enough. Not very strong. The points are not very closely clustered around the line, but it is good enough. So what will you say interpretation? The interpretation says that the scatter plot shows a strong positive linear, not very strong, but a strong positive linear association between hydrocarbon level and oxygen purity. When you are talking about correlation, you will not say which one is Y, which one is input, which one is output, just two variables. You are not interested in terms of correlation, which one is input, which one is output, just two variables, two random variables. The input output concept comes in regression, where X becomes the input, Y becomes the output. Okay. To confirm this observation that we saw from the scatter plot, the next question says, what does it say? Compute the correlation. Okay, the next question says compute the correlation. To compute the correlation, you will go to the formula sheet. The formula sheet will give you the formula of correlation to be something like this. What do you need for this formula? You need SXX, you need SYY, you need SXY. Okay, and the formula sheet will also give you these formulas. SXY equals summation XY minus summation X summation Y over N. SXX equals summation X square minus summation X whole square over N. It will not give you SYY. Looking at the formula of SXX, you have to write the formula of SYY just by replacing X by Y. I will write it in a different color. Can someone tell me the difference between this and this? Yes. The first one is the sum of square. The second one is the square of sum. The first one is the sum of square. The second one is the square of sum. Keep in mind two different things. So what do you need for these three sums? You need the summation xy, you need summation x, you need summation y, you need summation x square, you need summation y square, and you need n. So you will get them from the data. When I got them from the data, no more relying on calculators, lazy calculators. I got n equals 20 observations. I found the sum of X, it was 23.92. Sum of Y was 1843.21. Summation XY was 2214.6566. Summation X square was 29.2892. And summation Y square was 17044.5321. I got these five sums from the data. I plugged these five sums into these equations and I got the three SXS's. SXX came out to be 0.6809. SYY came out to be 173.3769. And SXY came out to be 10.1774. When I plugged them into the formula of correlation, R came out to be 10.1744 over square root of 0.6809 multiplied by 173.3769. And this gave me 0.9367. What do you say about this number? Strong, positive, linear association between X and Y. What is X? Hydrocarbon level. What is Y? Oxygen purity. So there is a strong positive linear association between hydrocarbon level and oxygen purity. Any question? Big portion of this question is about calculation, all about calculation. The next question says that fit a simple linear regression line. What does the word simple indicate in this question? In your course, you will use two words. Simple linear regression and multiple linear regression. What is the difference? Simple is one feature, multiple is chapter 12, many features. So the word simple means you are in chapter 11. The word multiple means you are in chapter 12 with more than one features. Fit a simple linear regression for oxygen purity. What is the Y variable? Fortunately or unfortunately, sometimes the student flips X and Y and all 5, 6, 7 chapter 11 are wrong. Usually what happens, they give you a data set and ask you 5 questions from that data set. And sometimes students call X to be Y, Y to be X, everything becomes wrong. So you need to really look for what is the output variable and what is the input variable, right? So here, what is the variable for which you are fitting the regression? Y, oxygen purity. Against what? Hydrocarbon level. This is X. This is X and this is Y. Using the method of least square, this is the only method we discussed. So write down the fitted equation. So we already have the sums. What is the formula for beta 1 hat? You will get it from the formula sheet. This is Sxy over Sxx. So you will plug in the values, and the values are 10.1774 over 0.6809. This is almost rounded up to 3 decimal 14.947. Similarly, beta naught hat is, this is given in the formula sheet, y bar minus beta 1 hat times x bar. I found the mean of y to be 92 point something minus 14.947 times I found x bar to be 1.196. And I got the intercept to be 74.2839. Now I will write it as an equation. So equation will be y hat equals 74.2839 plus 14.947 times xi. This is a fitted model. We call it a fitted model. Okay. Can someone tell me what is the meaning of 14.497? Interpretation of 14.497? Now the exam would not ask you for Y or X. Exam is asking you for purity, oxygen purity and hydrocarbon level. There is no X, there is no Y. You called it X and Y. So go back to the actual variables. If hydrocarbon level increases by 1%, as a result, the oxygen purity goes up or down. Why up? Plus sign of beta 1. By how much? On average by 14.947%. That is, if you move 1 unit to the right, you move 14 units up. This is 1, this is 14 point something. When X goes 1 unit right, Y goes 14 units up. What about the interpretation of the other number, 74.2839? Again,
when the hydrocarbon level is 0.
when the hydrocarbon level is 0,
Beta naught will be
the value of Y, yes, the average value of Y, the average oxygen purity of a sample where the hydrocarbon level is 0% will be 74.128. Is it correct? Is it correct? Is it correct?
mathematically.
Mathematically, yes. Practically, is it correct? Now tell me. Is it correct?
Not in the domain.
It's not in the domain. What will you say now?
Something has no.
It has no meaning. You will not interpret the intercept if x equals 0 is not in the domain. So you will say this quantity has no meaning. 74 point something, it has no meaning, no interpretation. Clear? If hydrocarbon level contains 0, then you would interpret it as the average oxygen purity when hydrocarbon level is 0%. But because 0% is not contained in the data, you will say this number has no meaning. Clear? Every question. Every question. Yes, outside the domain. Domain. You will look at the minimum of x, you will look at the maximum of x. If 0 is in between, you will interpret. If 0 is not in between, you will not interpret. For this question, the minimum is 0.95. If this minimum was minus 0.95, you would interpret.
Outside the domain, so it's not mean.
No meaning, yes. No meaning.
So,
Yes.
So in the last there was x equal to 0 and y equal to 0. Like the weight,
A data point?
yes, it's both are 0. Like if the weight is 0, the height is 0. I got 46, it's 47, 74.
Mhm.
Can I say
Average, not single value. This interpretation is about the average. If let's say hydrocarbon level 0 belongs to the domain, then you will not say that when hydrocarbon level is 0, oxygen purity will be 74%. Average oxygen purity will be this. The interpretation is about the average, not about the single value. Single value might be 75, might be 72. Okay. Next question. It will come as it is in exam. Anyone who can tell me what is required? Anyone who can tell me what is required? No.
The standard deviation of epsilon.
What is the standard deviation of epsilon? What is the notation that we gave to the standard deviation of epsilon? Sigma. Sigma, right? This is what we said. We said y equals beta naught plus beta 1 xi plus epsilon, where this epsilon follows normal distribution with mean 0, but variance is sigma square. So standard deviation is. Do you have sigma? How do you estimate it? Sigma hat. What is sigma hat? You never define in the formula sheet any estimator for sigma. You define it for sigma square. What was sigma square hat? You defined it to be MSE. You defined it to be SSE over n minus 2. Remember? The question is asking you for the square root of this quantity. The question is asking you for the standard deviation. This is the estimate for the variance. MSE is the estimate for variance. The question is asking you the estimate for the standard deviation of error, which is sigma. So again, go through that calculation chain. I will go through that calculation chain for getting SSE. For getting SSE, the first thing I need is SST, which is nothing but SYY. I found it in one of the slides earlier, SYY, and I got it to be 152.1216. Then I will find SSR. Formula sheet will give me that SSR is beta 1 hat times SXY. I computed all of these quantities earlier. Beta 1 hat is 14 point something. 14 point something multiplied by my SXY was 10 point something. So I get 152.1216. This is different. 173.3769. How do I get SSE now? $173.3769 minus 152.1216. So this comes out to be 21.2553. You see how short it is? I don't have to find the 20 fitted values, then 20 errors, then 20 squares of errors, and then sum. I can do it in 2 steps. Then plug it into the formula. Sigma hat will be 21.2553 divided by 18 square root. SSE divided by what is 18? N minus 2 square root. And the answer comes out to be 1.0867. The estimated standard deviation of errors. Next question. Estimate the sample to sample variation in B0 and B1 by using their standard errors. What are standard errors? What are standard errors? For X bar. Yes. For X bar, it was sigma over root of n. What about for B0 and B1? Standard error is what? Let me show you the formula sheet, and I want you to understand what is standard error and how do you get it from the formula sheet. Look at this formula. Where is the formula? Look at this formula and tell me what is the standard error of X bar. From this confidence interval, can someone tell me what is the standard error of X bar? It's the denominator of Z statistic, or the thing which is multiplied with the critical value. It is here. This one. What is this whole thing called? Standard error multiplied by the critical value. Margin of error. The whole thing is called margin of error. But the standard error is the thing which is multiplied with the critical value. What is the standard error of P hat? This is the standard error of P hat. Again, the thing which is multiplied by the critical value. What is the standard error of B naught? The thing which is multiplied by the critical value. What is the standard error of B1? The thing which is multiplied, or the denominator of T statistic. What is the standard error of Y naught hat? What is the standard error of mu hat of Y for a given value of X naught? So the thing which is multiplied by the critical value is the standard error. Here's the general formula for any confidence interval. It is the point estimate plus minus critical value multiplied by standard error. This is the general formula for any confidence interval. You will have the point estimate plus minus a critical value either from Z or from T multiplied by the standard error. So you will pick this formula of standard error from the formula sheet and you will go back. So the first thing you will do is you will take the formulas from the formula sheet and write it here. Standard error of beta 1 hat is MSE divided by SXX square root. Standard error of beta naught hat is MSE divided by 1 over n plus x bar square over SXX. Look at these quantities and see, is there any trouble in any of these quantities that you don't know how to find? Let me know if there is anything in this formulas that you don't know how to find, or you have not found it already in the previous 4 or 5 parts of the question. Have you found SXX already? Have you found MSE already? Have you found X bar already? Mean of X. For finding the intercept, you found X bar here. You found the mean of X. You found the mean of Y already. Even if you didn't, you know how to find the mean of X. You have a column of X. What is N? In this question, 20. Again, one of the mistakes that students make, they count the total number of values of X and the total number of values of Y, which is 40. N is not 40. N is the number of pairs. The total number of rows, not the total number of 2 times rows. Don't count it 2 times. Don't count X and Y separately. It's a 1 pair. So N is 20 for this question. So you just have to plug in the values and get the answers. When I plug in the values, I get the answers. I will plug in the values for you. So it gives me 1.1809 was MSE and 0.6809. So this gives me 1.3169. And then here, when I plug in 1.1809, 1 over 20 plus X bar was 1.196 square over. Where will we need these standard errors later if the question is about the confidence interval for beta naught or confidence interval for beta 1? You will need these standard errors. So that will be B naught plus minus a critical value from the T multiplied by the standard error. We'll continue with this example in the next class. I will start with part number 6, where you can see it is asking for the confidence interval. Before I wind up, can someone guess what is required in this question number 6? Average change in Y due to a unit change in X. What is that? Slope. So it is asking you for the confidence interval for beta 1, which is beta 1 hat plus minus T alpha by 2 n minus 2 multiplied by standard error of beta 1 hat. You already have beta 1 hat 14 point something. Critical value from the T table. Standard error, you just found it in the previous slide. You plug it in, you get the upper limit and lower limit. And from that upper limit and lower limit, you will say that we are 95% confident that if X changes, if hydrocarbon level changes by 1%, the average change in oxygen purity is between this and this percent, whatever are the lower and upper limits of this confidence interval. So let us wind it up here. Look at this question. I did not ask for the confidence interval for the value of Y when X is 0. Why I did not say it in terms of interpretation? Because I cannot interpret beta naught in this case, because hydrocarbon level 0 was not in the domain. So I did not ask this question in terms of interpretation. I simply asked it in terms of beta naught. But if in exam you get a question where X equals 0 is in the domain, they might ask you this question something like, construct a 95% confidence interval for the average value of oxygen purity when hydrocarbon level is 0. So that means beta naught. Okay. Here I cannot say that because I cannot write beta naught as the average value of Y when X is 0. So I'll continue from example number 6 in the next class, and I will finish this example in the next class, and then we will start chapter 12 in next week. If you have any questions from today's class, you can ask.